Hello, this is Team 26 of AI-based software engineering lecture. In this video, we would like to present about our project, GA-based test data generation for DOM Purify. DOM Purify is an open-source XSS sanitizer library written in JavaScript. For the detailed explanation of DOM Purify and XSS attack, we left the link of our previous proposal video link and some useful explanation of our project's background knowledges on the description of this video, so please check out. The goal of this project is to generate test cases that can concisely and sufficiently exercise the sanitizer measured in terms of code coverage. So, based on seed test data collected from domain knowledge, we applied genetic operators to generate various complex test cases. Then we constructed a test case generator for testing DOM Purify based on genetic algorithms. Those are the steps of experimental approaches and methods. We also covered them on the proposal video, but we will explain in more detail on this video based on our experience. So those are the experimental approaches and methods that we used. I will explain them step by step. So we first understood and learned about HTML tags and sanitization logic of DOM Purify. We first searched for HTML tags and attributes. HTML tag is the minimal unit of element composing a HTML document, and HTML attributes are the additional values given to tags that configures the tags or adjust their behavior. Then we looked for the sanitization logic of DOM Purify's implementation. It first parses given HTML document by placing HTML tags on each nodes. Then it iterates over each nodes, sanitizing elements by comparing its structure with malicious patterns, and sanitizing attributes by removing forbidden attributes and invalid values. After the end of the iteration, it returns the sanitized HTML document. Secondly, we developed a framework for parsing and manipulating HTML test cases. We used Python as our implementation language and used Beautiful Soup for the HTML and XML parser, allowing traversal and modification of parse tree. Thirdly, we extracted code coverage of DOM Purify's implementation with V8 coverage extraction functionality utilized with C8 report library. C8 report library helped us to use V8's code coverage extraction functionality by showing the coverage as a report. And lastly, we designed fitness function and genetic operators to generate test cases. The fitness function is as follows. The better the coverage of the test case is, the better it is. Also, shorter test case is considered as better one. And the coefficient beta multiplied here to make the effects are reflected equally. For the genetic operators, we have seeding, crossover, and mutation operators. For the seeding operator, we randomly generated HTML documents with tags and attributes with random string values. The HTML document size is determined with those properties: height, width, and attribute count, attribute value length. Also for the crossover operator, we randomly swapped HTML tags and attributes and HTML subtree and all attribute of HTML tags. And for the mutation operator, we deleted, added, replaced, or shuffled random HTML element, or we deleted, added, replaced random attributes, or we injected random byte to random position, stringifying them. The hyperparameters used for genetic algorithms are as follows. We used linear ranking for selection with S equals to 1.5 and 0.8 crossover rate and 0.1 mutation rate and population size 10.
To evaluate our results, we would like to answer the following 3 research questions. First, is the seeder effective in generating test cases with sufficient coverage? Second, does the GP implementation generate efficient test cases? And finally, does the GP implementation generate test cases in reasonable execution time? For the evaluation, we compared our GP test case generator's performance to random search and grammar-based fuzzer Tomato. For the random search fuzzer, it is a naive random fuzzer with strings generated randomly from printable ASCII characters. We run the test cases on DonPurify and evaluate code coverage metrics, feeding the evaluation results back to the test case generator. To test the effectiveness of CEDAR in generating test cases with sufficient coverage, we generate test cases for the three fuzzers with roughly equivalent length. Since Tomato generates test cases with length somewhere near 450,000 to 550,000 characters, this is chosen as the base length to generate test cases. For Tomato fuzzer, we choose the best possible coverage out of 100 test cases. For our GP implementation, we do not have a strict control over generated test case length, so HTML trees were generated repeatedly until we get a test case with length falling in the range. Parameters of height and width 7, attribute count of 2, and attribute value length of 2 to 5 were used. For random search fuzzer, we chose the minimum length of 450,000 in the given range, but V8 engine triggers out of memory for such dataset. This is predicted to be attributable for the parser attempting to parse a long L-shaped input. We see that the GP test case generator falls short of coverage compared to Tomato fuzzer by about 2.5%. Considering that we've chosen the best out of 100 Tomato generated test cases and are comparing it to the seed test case of our GP generator, we can say that our CEDAR is effective in generating test cases with sufficient coverage. To test the effectiveness of the GP test case generator in terms of both coverage and test case length, and the effectiveness of test case generators in terms of execution time, we generate test cases for the three fuzzers under fitness evaluation count limit of 100. To take into account both coverage and test case length, we choose test cases that optimize our fitness function the best. For random search fuzzer, we generate test cases with random lengths. For Tomato fuzzer, we use the aforementioned 100 test cases. For our GP implementation, we generate test cases with default parameters. We see that under the fitness function penalizing test case length, our GP test case generator generates test cases with best fitness compared to the other two. Tomato fuzzer generates test cases with best coverage, but the test case is several orders of magnitudes larger than the test case generated by our GP generator. Test cases generated by our GP test case generator has comparable length to optimal test case of random search fuzzer while achieving fitness of 72.12%. Considering both coverage and test case length, our GP generator generates efficient test cases. Also, the test case generation takes least time for our GP test case generator due to the structured nature of generated test cases requiring less random sampling than random search fuzzers, as well as less evaluation time compared to Tomato, benefiting from drastically shorter length. Thus, our GP generator generates test cases in reasonable execution time. The results are as follows. Random search fuzzer achieves reasonable execution time and test case length, but has worst code coverage. Tomato fuzzer, on the other hand, achieves best code coverage, but has worst execution time and length. Our GP test case generator has all the three characteristics of reasonable execution time, reasonable length, and reasonable code coverage. The future works that could be studied are as follows. First, we could apply more domain knowledge of scalable vector graphics, MathML, and JavaScript syntax. We could use grammar-based seed amputation as Tomato does while generating test cases. Also, we could apply this to other sanitizer libraries such as HTML Purifier and Lucy XSS. Finally, we could apply this research to browser DOM parsers, which are much more complex than server-side XSS sanitizers and may reveal mutation XSS patterns only visible at client-side. This is the end of our final presentation. Thank you for watching.